right, so today we are learning how to factor using what's called the difference of two squares. I like to call it dots. Difference of two squares, dots, D-O-T-S, right? So this is the fourth day of notes for chapter 5. We are going to break after this set of notes. We are going to review tomorrow. We're going to review Monday, and you are going to take a quiz on Tuesday of next week.
When's our test?
I don't even know. A long time from then. I only plan 1 week at a time. So not next week is the answer. All right, let's review. So do you guys remember how to multiply something like this? It's a binomial times a binomial.
Yes. Wouldn't you do x times x and x times 4?
Yes, we do. We called it double distributing. So we take the first x, the first term in the first set of parentheses, and we multiply it by both terms in the second set of parentheses. So we do x times x, then we do x times the positive 4. Then we distribute the negative 4. So negative 4 times x and negative 4 times 4. That gives us these 4 terms. What happens to the 2 terms in the middle? They go away. That gives us 0x. You don't need to write that. Your answer is just x squared minus 16. So we started with a multiplication problem. We multiplied it out. We ended up with x squared minus 16. Do you see how these are both perfect squares? You got them from squaring another number, and there's a minus sign in the middle. So today what we're actually going to do is we're going to start here, and you're going to give me this. I know. It's going to be awesome. Let's practice multiplying through some more, though, so you start to see the pattern. Yes, we're writing it as the multiplication problem.
So we're factoring it back into the double distribution.
Yes.
That's weird.
Let's practice the double distributing, though, a little more. So when you double distribute on this one, what do you end up with? We distribute the a. What's a times a?
A squared.
What's a times positive 7y?
7a.
7ay. And then when you distribute the minus 7y to the a, what do you get? Minus the 7ay. And then minus 49y squared. Once again, where does that middle guy go? What's happening? Yeah, those go away. It equals 0ay, which is nothing, right? So you don't even need to write it. This only works when you have a minus in the middle here. Or when these two signs are different, okay? Depending on which way you're going.
What if it was plus minus?
If this one was plus and this one was minus, it would still work. You would just end up with negative 4x plus 4x, and they'd still give you 0. If this was a plus and you were doing the process we're going to practice today, the factoring, it doesn't work. There's no such thing as a sum of two squares. It's only difference of two squares. So you got to look for the minus sign today. All right, last practice. All right, so what happens on this one? You get 16 minus 12m plus 12m minus 9m squared. Good. So this is what we were just talking about. It doesn't matter if the plus or the minus is in the first binomial or the second binomial. You can flip-flop them. It still works, okay? This guy always ends up negative because of the fact that the signs are different, okay? So you end up with 16 minus 9m squared. So this is last semester stuff. We should all be good on this, right? But this kind of reminds us why today works out so well. So it's a nice little review. All right, next I want to talk about what it means to be a perfect square. A perfect square means that one number times itself, one number squared, gives you that number. Is there a number when multiplied by itself that gives you a 4?
Yes.
Yes. What is that?
2.
2. So 4 is a perfect square.
Yes.
Is 8 a perfect square?
No.
It is not. There is no number times itself that gives us an 8. So that's a no. 100. Yes. What would it be?
10.
10. X squared.
Yes.
Yes, that's just x times x. Good. A to the third. No. Y to the fourth.
Y squared.
Yeah, y squared squared. So this one's a yes.
So why
A to the third is not. Because there's no number times itself that would give us a to the third. No, you couldn't square anything and end up with that. Thank you. All right, so we already kind of talked about these. What does it mean to be a difference of two squares? You have to have both parts. It has to be a difference. So we need a minus sign. There has to be two numbers, and they both have to be perfect squares. Difference of two squares. All of those things have to be there for this to work. It's a very specific type of setup that you need to use difference of squares. Any questions? All right, here's our first example. All right, so whenever we do this, I'm going to do the first one by hand, and then the answers are going to start popping up after this one. So you need to think of what number times itself gives you this, what number times itself gives you this, and is it a minus? Is it a minus?
Yes.
Can you think of a number times itself that gives you x squared?
Yes.
X. Can you think of a number times itself that gives you 25? 5. So when we break it down, those go in the front. This guy goes in the back. One gets a plus sign, one gets a minus sign. They're both binomials. If you put the minus in the front and the plus in the back, I don't care. Okay? Same thing if you ask me. What are your questions? Everyone always says, is it that easy? It's that easy. Okay?
So if we just write that.
I don't need to see the arrows. I don't need to see like some factor tree for 25. Go for it. Okay? These are very quick problems. Write this one down. Start to ask yourself, do we have the right setup? We do.
Would the number just go in front?
Mm-hmm. So what do I have in the front? 11. What do I have in the back?
8.
One gets a.
Plus.
One gets a.
Minus.
That's it. Now, you can't put the A in the front even though you might want to, because when you double distribute it back out, the 121 would be the negative term, and we can't do that. So you got to keep them where they are. This one's positive, it goes in the front. This one's negative, it has to be in the back.
So it's not the same. So a squared minus 121 isn't the same as 121 minus a squared.
Correct. The signs are backwards. All right. Is it a difference of squares? First question.
Yes.
Yes. How would I make, like what number times itself would give me 16x squared?
8x.
Careful, you have to multiply.
8x.
8 times 8 is 64.
4x.
4. 4 times 4 is 16. So we have 4x in the front. What are you going to have in the back of each binomial?
5y squared.
5y squared. You take half of them. Good. One gets a plus sign, one gets a minus sign. Questions?
So it doesn't matter which one gets the plus and minus.
Nope. Anyone have it? Yes.
9a minus 4y on one side and 9a plus 4y on the other.
Very good. Make sure you use parentheses. Make sure it's two binomials right next to each other so you're multiplying them. Trying to get tricky on you. It is a difference of squares. What number times itself gives you 1 over 9? 1 over 3. Good. And then, of course, just r and r, right? In the back, 2 over 5 with the t. Good. Perfect. Give one a plus, give one a minus. Questions? All right, give this one a shot. Anyone think they have it? Yes, ma'am.
8 y to the second minus 5t and a1 to the second plus 5t.
Very good. She had the minus in the front and the plus in the back. I had the plus in the front, the minus in the back. It's the same thing. All right. Now we're going to take what we did yesterday and what we did today and kind of mix them up. Is this a difference of two squares?
No.
It is not, but can I do something else that I know how to do?
Yes.
Yeah, what am I going to do on this one?
Divide it by a GCF.
The GCF. This is a GCF problem. Good. If you need to do a tree, go for it.
3.
3, 15. 25. 3, 25. For 75.
Wait, what?
3.
You're trying to do a dots, I think. Oh, you want to do a factor tree? Okay, well, I can do a tree. Sorry, I thought you were already telling me the GCF. I was like, what? What? Okay, yes, we can do a tree if you'd like.
Just 3.
So, yes, looking at their trees, the prime factorization is 3 times 5 squared for 75. The prime factorization for 12 is 2 squared times 3. So what's the GCF going to be?
3.
3. Good. Now when I click, the GCF's going to pop up. The factor trees are going to go away. Is everyone cool with that? Okay. Now, I divide everything by 3. I write the 3 in the front. Oh. Well, that's a pretty looking problem. What's so glorious now?
Huh?
What's so glorious now? Now it's a difference of squares in the parentheses. What? So you can do another round of factoring. You keep the 3 in the front, and now you break this guy into 2 binomials. What's the first one look like? 5x minus 2, 5x plus 2. Good. So some of these you can do it, you can do factoring more than one way and more than one round of it. So we did a GCF round and then a difference of squares round.
You just keep
Just keep the 3 in the front. Now, if you wanted to multiply this one out, you would double distribute and then distribute the 3. Or you could distribute the 3 first and then double distribute. Either way, you'll end up right back here.
That's how you check your answer.
That's how you check your answer. Very good. All right, here's B. All right, anyone have any thoughts? It's not a difference of squares. 9 does not work because that would have to be 99 and not 98.
I guess 2.
No, it has to be not.
I feel like there's a bigger one than 2. If we're stuck, let's just do some trees real quick. So this is 8 and 9, 3 and 3, 2 and 4, 2 and 2. So 2 squared, no, 2 to the third times 3 squared. In the back, what is it, 249?
Yeah.
7, 7.
So it's
So it's just 2, right?
Yeah.
Oh, I swore there was a bigger one. Okay, good deal. Just 2, right? Can the trees go away? Okay. 2. It's amazing. Oh, I see what's happening. Do we have to,
Change the z to the 6, the z to the 3rd.
when you do what?
When we do the second round of
Oh, so you want to do difference of squares now?
yeah.
Yeah, so half of those z's have to go in the first one, half of them in the, so it'd be z to the third. Yep. So yes, this one works out just like the last one. You're left with a difference of squares. So how would you make 36z to the 6th? 6z to the third. How would you make 49? 7 and 7. There we have it.
What
Mm-hmm.
if we ended up with another perfect square?
Then you could keep going.
Yes, that's a perfect square.
Yes, it is. What do I end up with on the...
A to the 4th plus 9b squared.
Keep going.
Oh, and A to the 4th minus 9b squared.
Very good. So you have an a to the 4th plus 9b squared and a to the 4th minus 9b squared.
I thought 8 wasn't.
81.
No, I mean 8. Like
What?
A to the 8.
Oh, so 8 isn't a perfect square, but it is an even number. For the exponents, we check to see if it's an even number. Not it. You don't take the square root of this. It's not what number times itself gives you the 8. It's just half and half for the exponents. because we add the exponents when we multiply with like bases. Okay,
Yeah.
you can do it again. Can I do it again here?
Yes.
Break
No,
my
no,
heart.
I'm sorry.
You cannot. There's no such thing as a sum of two squares. I mean, there is such a thing. Here it is. It's what it looks like. But it doesn't factor. Okay? The one that factors is the difference of two squares. So in the front, that guy stays the same. We have a to the fourth plus 9b squared. What would I have in the next set of parentheses?
A squared plus 3b.
A
A squared minus
squared minus 3b. Very good. Yes, sir.
So what would happen if it was another perfect square?
You keep going. You keep going until you have no more difference of squares. All right. Uh-oh. It's a difference. It's not perfect. Do we need to do a tree or somebody think they have it?
Yeah, true.
Let's do a tree. Okay. 243 is divisible by 3. What is 243 divided by 3? What is it? 81. Okay. 9 and 9. 3, 3, 3, 3. Holy moly. So 3 to the 5th power? Okay. In the back, what, 2 and 24, 2 and 12, 2 and 6, 3 and 3? No, 2 and 3, sorry. I lied. So this one is 2 to the 4th times 3. All right, what do they have in common?
3.
Just a 3, 3 to the 1st. Can I get rid of my trees? The trees are a nice, like, off to the side, maybe on scratch paper sort of a thing. But it's nice to keep it clean under here so then you can go divide by 3, divide by 3. All right, so I have a 3 in the front. What did we say that was, 81?
Yeah.
All right, so I have 81m to the 4th
81 to the 6.
minus 16. Okay, this
Why did you
is
get 81
nice.
M to the 4th?
Because I had an m to the 4th.
Why did you cut the 4 in half?
When I do dots, I'll cut the 4 in half, but I'm doing GCF right now.
Oh.
Yep, don't mix them up. We didn't do anything with the ends yet. We just divided the coefficients by 3. We wrote a 3 in the front. Blah. Getting tongue-tied. All right, 81m to the 4th minus 16. Does that feel special to anyone?
Yes.
Yeah, that's a difference of squares. So what am I going to get on my next step? 9m to the 2nd minus 4. 9m to the 2nd plus 4. And don't forget your
3.
3 in the front. Good. It's very easy, step by step, to drop that 3. Please don't do that, okay? Keep an eye on him. Uh-oh. We're not done.
Oh.
We got another difference of squares.
3M.
3m minus 2, 3m plus 2. Again, 3's still out here. This is a plus, so we can't do anything with it. Sum of two squares is not special. SOTS isn't something we get excited about, okay? But, yep, now we're done. SOTS, that's funny. Sum of two squares?
Sots.
It's not special. It's not like dots, difference of two squares. All right, we good? Sorry, just cracking myself up with the lame math jokes. Okay.
Perfect square.
Yes.
No.
The 16 is a perfect square, but we don't have a minus sign. When I don't see a difference or a minus, my radar just turns off to the squares. Don't even care.
So it's A.
Just A. This is a GCF problem, just A. Now they're perfect squares, but do I care?
No.
Still don't care. Still a plus sign, still nothing to do with it.
So you're done.
Don't fall into that trap. Questions?
So you just leave it like this.
Leave it alone. That's the answer. Hmm?
So only
It's a good one.
perfect square.
These are perfect squares. There's two of them. There's a minus in the middle. Perfect dots set up. What's the next one, next line gonna look like?
4x
A,
to
A.
the
Oh, she's
Oh,
going.
4x to the second minus to the second.
Minus z to the second, and then again with a plus. Good. Okay, am I done? Which one needs a little more attention? Yes.
The second one.
The second one, the one with the minus. Good. So that one stays the same. He's done. Can't do anything with it. Then what?
2x minus
2x minus z, 2x plus z. Order doesn't matter. Questions? Don't you love difference of two squares? I do.
It makes it a lot easier.
Yeah.
It's a lot of steps though.
Yeah. All right. What we talk about today?
Dots.
Dots. Now, I will tell you, not every teacher calls it dots. I don't know if it's something one of my teachers did and now I do it, but I've said it to other teachers like, oh, I'm doing dots today. And they're like, what are you talking about? So, yes, we're going to call it dots, but I will warn you, universally in the math world, it is not always called dots, but it is always called difference of two squares. Any questions on dots?